Welcome to Cyclopod, showcasing work by early career geoscientists that is of interest to the cyclostratigraphic community. This podcast is made possible thanks to financial support of the International Subcommission on Timescale Calibration.
Hi there, welcome to the 10th episode of Cyclopod already. Last month, we looked into insolation patterns at low equatorial latitudes. We talked about the fact that the Earth is directly overhead twice per year in the intertropical region and how that might be a driving factor for half precession cycles. This week, we remain in the intertropical region and we make an excursion to 11 degrees south, offshore Brazil. And our guide for today, who will guide us through Brazil, is Jaqueline Ferreira. She's a master's student from the University of Sao Paulo, and she obtained her master's degree in 2021. In the framework of her master thesis, she studied a sediment core of the São Francisco River. So this sediment core goes back 45,000 years in the past, and that core allows for a detailed assessment of the astronomical scale variability, as well as the millennial scale variability of climate and vegetation in the hinterland in Brazil. And that is really cool because that hinterland is made up by a mixture of forest, savanna, grasslands, and so on. So what Jaqueline did is she looked at different proxies to reconstruct how climate and vegetation changed over the last 45,000 years. First of all, Jaqueline, congratulations on the publication of your paper in Quaternary Science Reviews. It was really a pleasant read and very welcome to Cyclopod as well. Before we dive in, can you describe how the São Francisco River drainage basin looks like today?
Hi, David. First of all, I would like to thank you for inviting me. I'm very happy to talk with you today about this story. Well, the São Francisco River Basin is the largest river system in Western South America. The source of the river is in the Serra da Canastra, about 20 degrees south in southwestern Brazil, and the river flows northward until about 10 degrees south. The headlands of the basin are under the influence of the South Atlantic Convergence Zone, a distinctive feature of the South American monsoon system that dominates the seasonal precipitation cycle in South America. Due to this influence, the headlands of the river are wetter than the rest of the basin, and the wet season is in the austral summer, between December and February. This region is of great ecological importance due to its extension and because there we also found part of Cerrado, Caatinga, and Atlantic Forest, very important Brazilian biomes.
Oh, can you say a little bit more about these unique Brazilian biomes?
Atlantic Forest occurs mainly over the southern portion of the basin. Caatinga occurs predominantly in the north and is the only exclusively Brazilian biome. The name Caatinga is a Tupi word in indigenous languages meaning white forest. It is located in the semi-arid region of Brazil and is a kind of tropical dry forest. The central portion of the basin hosts a large portion of Cerrado biome, a complex ecosystem with mixed trees and grasses. The density of tree cover has profound ecological importance in the Cerrado. One of the major ecological questions of our times now is whether tree cover responds smoothly to climate change and other stressors or exhibits sharp and extreme transitions. I believe that is the importance of a study like ours, where we can relate past environmental change to change in the sedimentary record.
Wow, yeah. I think there is indeed ample motivation to study changes within the São Francisco River Basin. And a marine sediment core at the river mouth, that is, of course, the perfect place to look. So can you describe how that sediment that you studied, how that sediment looked like?
Yes, sure. We analyzed a marine sediment core collected from the continental slope of western South America near the São Francisco River mouth during the RV Meteor Cruise M125. The marine core recovered about 10.4 meters of sedimentary material, collected at a water depth of about 1,900 meters, at the position 11 degrees south. The section that we analyzed consisted of predominantly dark greenish clay, rich in pyrite, and organic carbon. In this core, the transitions between Holocene and Pleistocene sediments appears as a color change from brownish, more calcareous clays to dark, grayish carbonate pore clays.
And so once you took the samples, the analytical part could start, so the proxy work. What exactly did you measure on those sediments to base your environmental reconstructions on?
To answer our questions, we choose to work with long-chain alkanes. Long-chain alkanes are produced by terrigenal plants, so the isotopic information of these molecules provide important answers to the continent's environmental questions. They are composed of hydrogen and carbon. The hydrogen isotope composition of these molecules is well correlated with the hydrogen isotope composition of rainwater. In alkanes, the variation in the hydrogen isotopic ratio indicate variations in rainfall intensity during the wet season. Carbon isotopes, on the other hand, indicate the type of photosynthetic pathway, as metabolic difference results in different carbon fractionation. C3 plants have a higher proportion of light isotopes on the constitution.
And thanks to the 914C date, so carbon-14 ages, you obtained a high-resolution time series covering the last 45,000 years. Is that correct?
Yes, that's right. The investigation section of the core, the uppermost 4.7 meters, cover the last 45,000 years and shows an average sedimentation rate of 10.4 centimeter per 1,000 years.
What I find intriguing in your study, Jaqueline, is that neither your carbon isotope curve nor your hydrogen isotope curve exhibit a precession signal. That seems counterintuitive at first, at least to me, for such a low latitude setting. How did you interpret this lack of precession?
This is a great question. You know, the San Francisco River basin starts at 20 degrees south and flows into the sea at 10 degrees south. So it basically has a pretty large latitudinal range. So we note that precession is a strong control on rainfall and monsoon domains. Indeed, the South American monsoon system intensity is dominantly influenced by changes in austral summer insolation. That in turn is strongly associated with the precession cycle. In a precession-drive high austral summer insolation situation, a stronger South American monsoon system would intensify the circulation pattern, increasing precipitation over the western Amazon and under the South Atlantic convergence zone, and increasing aridity over the northwestern Brazil. In short, it is an antiphase pattern. Because of the opposing hydroclimate influences of the southern and northern hemispheres of the San Francisco River, speleotene-based precipitation records from the central portion of the basin also showed no clear precession-driven changes.
Yes, but your carbon isotope curve, which is your proxy for trees versus grasses, that does show a strong obliquity imprint. Why could that be?
Yes, we found that carbon isotopic variation was well correlated with variations in obliquity. And that was a surprise. We really did not expect this at the beginning of our study. The thing is, changes in the tilt of the Earth axis, so the obliquity, modulate the temporal and spatial distribution of insolation. So the obliquity influences the amount of insolation received at high latitudes. Under maximum obliquity, positive insolation anomalies occur in the high latitudes of the summer hemisphere, and negative insolation anomalies occur in the winter hemisphere. To balance these changes in incoming energy, there is a strengthening in the Hadley cell of the winter hemisphere during maximum obliquity. This strengthening increases the cross-equatorial moisture transport into the summer hemisphere, pushes the intertropical convergence zone towards the summer hemisphere, and increases the strain of trade winds in the winter hemisphere. Our data indicates expanded C4 vegetation under minimum obliquity and expanded C3 vegetation under maximum obliquity. We suggest that this shift from savanna and grasslands formation to forest formation was related to a decrease in dry season lands induced by the effects of the obliquity on the climate dynamics that I have just described.
What you explained just now with the interhemispheric moisture transport and so on, all of that's backed up by climate modeling, right? Can you tell us what kind of simulations you ran to test the role of obliquity on precipitation patterns?
Our idealized experiments were performed to show the impacts of maximum and minimum obliquity. The eccentricity was set to 0 to have no impact of precession. We used the community Earth system model and we performed experiments for both obliquity extremes and analyzed the precipitation anomalies for different seasons. We found significant precipitation anomalies during austral autumn at high obliquity in the region of the San Francisco River. Autumn is the season after the rainy season in this region, which is the summer. So an increase in rainfall in autumn results in an increase in the wet season land, a favorable environment for the expansion of C3 plants in this region. In low obliquity, there is an increase in the dry season land, favoring an environment for C4 vegetation. Also, to test this suggestion, we compared the modern distribution of these vegetation types to instrumental data. And we found significant values that indicate that a longer dry season land increases the stability of savanna and grasslands formations, and that even a small change in seasonality is enough to influence the arrangement of vegetation types.
Your work really adds a whole lot of new insights in our understanding of how these savanna environments respond to climate change. So, can you make inferences for man-made climate change, climate warming? Can you say something about that?
The poleward expansion of the Hadley cell is anticipated to have a number of regional climate impacts in the subtropics. Potentially, the shift of the subtropical dry zone, which corresponds to its descending branch. So this may result in the extension of these arid regions to higher latitudes. Models also indicate that it's likely that the tropical belt has widened. And also that it's also expected that the occurrence of the extreme weather events such as severe drought on the one hand and precipitation extremes on the other will increase in the near future. Thus, we attempted to highlight the possible outcomes of such changes in regional precipitation based on paleo records. Since paleoenvironmental records, such as those in our study, provide a long-term perspective on understanding the controls, magnitude, and spatial temporal aspects of climate change and impact on tropical ecosystems.
It's time for the number of the month. This month, the number is 387. IUDP Expedition 387, titled Amazon Margin, is an expedition that should have sailed a few years ago. But it has been postponed because of several political problems. Your co-author, Cristiano Chiese, was supposed to sail on this expedition. I think we all hope that this expedition will be able to take place soon after all. But Jaqueline, tell me, why do you think it is super important that this expedition is taking place soon?
About this expedition, I want to mention that it is delayed due to technical issues, but the Brazilian colleagues are very close to getting all the necessary authorization. So I guess the expedition will happen soon. I hope so. And it is very important as it is expected to recover the longest continuous 55 million year record of the Amazon River. With this, it will be possible to reconstruct the biodiversity of this region as well as the evolution of the landscape and the climate of the Amazon and the equatorial Atlantic in the Cenozoic. So these are highly expected records and I can't wait to see what they will reveal.
Back to the science now. I want to know more about the hydrogen isotopes you measured. They don't show precession, but also no obliquity, but they do indicate weather conditions during Heinrich stadials.
The heritage stadiums are associated with increased austral summer rainfall over western tropical South America due to an anomalous cyclonic circulation and moisture transport from the warmer South Atlantic onto the continent. Our hydrogen isotope data indicates increases in the intensity of precipitations in the wet season during these events. So these are very important results.
But your sediment core is not the only archive that shows this pattern, correct?
Exactly. Studies on speleothems from caves in the central region of the San Francisco River Basin also indicate the same pattern of intensive precipitation events during the heritage stadiums. Also, the titanium-calcium ratio data on the same marine core that we analyzed indicate an anomalous increase in the proportion of terrigenous versus biogenic sedimentation associated with the heritage stadiums, which indicates precipitation anomaly events as well.
But not all Heinrich stadials show the same precipitation pattern, apparently. H1 and H4 show a different pattern compared to H2 and H3. Why is that?
Our carbon isotope data suggests that millennial scale changes in vegetation in the region are modulated by obliquity, and different heritage stadiums shows a distinct response depending on the obliquity phase. So heritage stadium 4 and 1 occurred during high obliquity when dry season land was shorter. Under this obliquity configuration, increased austral summer precipitation fostered forest formations to spread throughout the basin. On the other hand, heritage stadium 3 and 2 occurred during low obliquity, when dry season land was longer. This obliquity configuration led to savanna and grasslands formation to spread even under increased austral summer precipitation. So, this indicates that seasonality primarily describes the response of vegetation to variations in wet season intensity, and the dry season land is the driving factor in the long-term distribution of forest versus savanna and grassland formations in western tropical South America.
Thank you very much, Jaqueline, for telling us about your recent paper in Quaternary Science Reviews. I'm really intrigued by the fact that precipitation and vegetation proxies are not one-on-one. They show slightly different patterns. And it's really impressive how Jaqueline has been able to disentangle all that. Really good use of multiple proxies and the integration of climate modeling to help with the interpretation. Thanks again, Jaqueline, for your time. And I also would like to thank you for listening to the 10th episode of Cyclopod. See you next time.